Hi, my name is Carlos M. Ortiz Marrero. I'm a data scientist at Pacific Northwest National Laboratory. Today I'll be talking about some joint work I did with Nathan Wiebe and Maria Kieferova on entanglement induced barren plateaus. So the main motivating question that we were trying to answer was, can we efficiently learn and generate quantum states using parameterized quantum circuits? And I believe this is a question at the heart of quantum machine learning. And we were interested in understanding what were the capabilities of such a paradigm, but also trying to get a better understanding of also what are the limitations. One of the big limitations in the field of quantum machine learning right now is the phenomenon of barren plateaus or vanishing gradients. And the summary of this talk is basically that we've managed to find a relationship between excess of entanglements between visible and hidden units of a model and this barren plateau phenomenon. So to give you an idea of what we mean by parameterized circuits, or another term used is quantum neural networks. Here's a couple of definitions of some of the models that we're going to be looking at. The first model is the unitary model. We have that model here on the left. And this model is basically what happens when you have a quantum state and you apply a sequence of unitary gate operations. In particular, the gate operations that we're going to be looking at are of the form E minus I H K theta K, where theta are the parameters of the model that we aim to tune. And HK are the Hamiltonian terms to specify a particular quantum neural network or parameterized circuit. Another class of models that is interesting are the quantum Boltzmann machines. These are quantum generalizations of classical Boltzmann machines, where we have linear combinations of Hamiltonian terms, Hi, theta I. So we have the sum and then matrix exponential of such terms, and then we're normalizing by the trace of such a model. To give some intuition as to why these models are sometimes called quantum neural networks, let's just look at the case where we compare it against a classical neural network. So if we look at a classical neural network, we have a sequence of n inputs here. And then what happens is that we do weighted linear combination of weights, interacting weights that we see here, followed by some sort of nonlinear activation function. And then that produces a hidden number, when we do this over multiple nodes, we have a hidden vector, h1 to hn. So more succinctly, we can represent this here at the bottom, where we have our input x. This is the vector of x1 to xn. Then being multiplied by a weight matrix, which corresponds to these W11, W21, and then element-wise action on each one of the elements by some sort of nonlinear activation. And this is the basis of a classical neural network. When we look at the case of a quantum neural network, more specifically of the unitary model, we see that we have a sequence of qubits, and then we have, in this case, gate operations interacting between two qubits at a time. And if we sort of see what does this mean, or what's this look like when we write it down, we see that we have our vector h being acted upon by unitary matrices, and then this produces a hidden state, or we're going to call this a hidden state for now, or a hidden representation. And it's worth pointing out that in this case, the order of operations of these unitaries matter. We're going to be looking at systems, or as we're going to be looking at our model as interacting between the visible system or visible subsystem of our model and the hidden subsystem of our model. So let's start defining what do we mean by that. So by the visible units of our model, we just mean the units that at the end of the computation we measure out. So these are going to be our visible units. And by our hidden units, these are the qubits that we use during our computation, but we don't really measure when we end a computation. Formally, one way of writing this mathematically, or getting a better understanding of what is the actual output that we get out of this circuit, is by writing down the reduced density matrix. And we're going to denote that by rho v. And that is just what happens when we trace out the hidden subsystem, or the hidden qubits that we're not going to be using of our underlying model. And here's just one representation when we're when rho theta is the density matrix of our output of our circuit, and rho v is a reduced density over our visible subsystem. So let's talk about what do we mean by Barren Plateau and what is this actual phenomenon. So in 2018, McLean et al. Published a paper where they were looking at various classes of parameterized quantum circuits, or quantum neural networks, and they noticed that for various classes of models, the probability that the gradient along any direction, the probability that the gradient along any direction is non-zero for some fixed position is exponentially small as you increase the number of qubits of your model. So this has a lot of problems when it comes to scalability, as you want to get you want to increase the number of qubits of your model and understand more and more complicated behavior. And here we see just a plot of a plot containing one of their numerical results showing this. So we're pointing out that this phenomena this happens classically. It might happen in a slightly different context, but for recurrent neural networks, it was known that when we were trying to back propagate through a recurrent layer, when you try to back propagate through this layer, if your intermediate steps were small, your resulting final gradient is also going to be small. And you would see in training or in practice, what you would see is plots like the one that we have here on the right, where your training loss, or your training accuracy would start increasing, and then it would stop, and the model would just stop learning. Another result by Maria and Nathan is that they noticed that for quantum Boltzmann machines, increasing number of hidden units wasn't really helping when they were trying to learn certain tasks for various quantum Boltzmann machine models. And they documented this for two models, and we can see here that for the model that represents Q here, for an increasing number of hidden units, we see that their metric that they were optimizing doesn't really give you more predictive power as you increase the number of hidden units. So what we did is we took into account this observation by McLean that models, as you increase the number of hidden units, have exponentially small gradients, and the observation that adding more hidden units wasn't really doing anything to help our models learn. And we started studying this question a bit more in depth to see if there was any relationship between the two. We start by first diving into the thermalization literature by considering our model as a bipartite system, where one subsystem would be the system corresponding to the visible subsystem, and another subsystem would be the system corresponding to the hidden subsystem. And if we study that question that way, we get that when we look at our reduced density matrix corresponding to our visible subsystem and we compare it against the maximum mixed state of the corresponding dimension, when we look at the trace between those two things, the expected value of this quantity can be bounded by 1/2 square root of dV divided by dH. And this is leveraging a result by Popescu et al. From 2006. So for the unitary model, we did some experiments just to see what this would look like for that model. And here we ran a sequence of 1,000 various instances of our model compared against the maximally mixed state for models that have 6 units or 10 units, where we fix the number of visible units and we would increase the number of hidden units. And if this result were to hold, we would see that the expected value would get smaller. And we see that's the case here in the picture on the right here, on the top right. Another picture is that if we look at an increasing number of units by fixing the number of visible units, here the x's correspond to the average value, basically, of these histograms. And we also see that things are, the average value is decreasing, validating the result here. And here the orange line just corresponds to that bound that we just showed here. So with that, we started to dive into what this result or results like this, how can we use those results and apply it to the gradients of these models. And we managed to show that under some mild assumptions, we get exponentially vanishing gradients as we increase the number of hidden units. So more formally, let's define delta K as this quantity that we have here, where HK is just the vector corresponding to all zeros and 1, and the 1 corresponding to the K, and the 1 in the K direction. And for any Hermitian operator that we're going to denote by O of objective, acting on that visible subsystem, when we considered objective functions of the form trace of the Hermitian operator acting on the visible subsystem of our state. So in this case, we're considering the unitary model of states, rho theta minus rho theta plus delta K, so this perturbation. The expected value of this quantity is an Lipschitz continuous function on the perturbation with a constant lambda here. And this constant scales like root dV over dH, which is similar to this result that we saw by Popescu et al., which some terms, so particular infinity norm of the objective function times the infinity norm of the term that corresponds to the kth dimension. So we attempting to look at small-scale numerical experiments for other types of objective functions. So particularly if you look at the fidelity, when we look at the gradient, the infinity norm of the gradient of the fidelity, and we compute the variance of an ensemble, we start seeing that for a fixed visible dimension, in this case a dimension of 8, as you increase the number of hidden units, we start seeing a decrease in the gradients, in this overall behavior of the gradients. So the gradients start getting smaller and smaller. We also looked at the quantum Boltzmann machine. Although in this case, the assumptions were slightly a bit more nuanced. So again, under some mild assumptions on H that we have the details in our paper, let's define HK by being of the form HV tensor HH. So and let's suppose that HK is an elementary tensor of this form, living in the in CD times CD. CD times CD. D here is the product of dV times dH. And let's define rho theta k to be e to the minus h plus theta k times hk, divided by just this normalizing factor of this function over here. And let's define a observable O of G that lives in the visible subsystem, that acts on the visible subsystem. And let's define kappa to be the trace of the observable tensor identity on the hidden subsystem acting on our rho that we define here. So we see that with these assumptions, this trace here is a differential function that obeys where the derivative obeys the following scaling. So if we take the derivative of this k kappa along the k dimension when theta goes to 0, we see that this derivative also follows root dv divided by dh. But here the terms are a little bit much more complicated. So we have these terms inside the square root. We again see that we have the infinity norm of the objective function times this parameter that characterizes the inverse minimal gap of our Hamiltonian times the infinity norm of HK. So again, we attempted to validate this for other objective functions, in particular the trace distance here, for some small numerical experiments, and for fixed for states with a fixed visible dimension, we started to increase the number of hidden units, and again we see a decrease in the gradients as predicted by our theorem here. So as we increase the number of hidden units, our gradients get smaller, which we sort of see that should be the case. So with that, let me just talk about some follow-up work and some open problems that I think are interesting. I think one of the problems that I think is interesting is, there's all these Barren Plateau phenomenons. We just added a new result to that ensemble of papers talking about this. More interesting question now is like, what can we do about this? What training routines can we come up with, and what objective functions can we construct that can maybe bypass some of these Barren Plateau phenomenons? Alternatively, another way of thinking about this question is like, what type of quantum architectures do we need to use to maybe bypass this or alleviate this problem? So here at the bottom we have this is the references to the paper that I just talked about today. We have another paper in the archive that's coming out very soon that actually attempts to address this question that we see here. So with that, thank you very much for listening to my talk. And if there are any questions, please feel free to reach out at the email that we see here. Thank you very much.